Okay, so today's lesson kind of links to what we've been doing, except at the beginning, it looks like we're going to work with our natural base, the base E. So we're going to look at properties of logs with base E, and they work the same way. So if we take this, ln of e to the fourth, and we talked about yesterday, one of our properties was that we can take this exponent and rewrite it as multiplication. Let me change colors so you can see it. So, is that fair? Can that exponent come out in front? Sure. Now, hopefully you remember, we've done this. Natural log of e. Well, natural log means log base e of e, doesn't it? Isn't that our shortcut for this? Well, what power do you raise the e to get e? 1. Natural log of e has a value of 1. So whenever I have natural log of e by itself, I'm going to replace that with 1. And what is 4 times 1? 4. Yeah, that's pretty much it. So, same thing here. When we have natural log of e to a power, that power, we can use those properties that say we can take that power and rewrite it as multiplication.
So you just get your your power.
Okay, so the answer ends up just being the power. Now, I will never teach a shortcut. I always, always, always teach for understanding. Because if you can understand it, you have a better shot of remembering it. But what you're going to notice every time we have natural log of e to a power is the answer is just the power. That's what it ends up being. But this is why. Because this can be rewritten as this, and we know that this has a value of 1. So that's the answer.
I already knew that. Apparently.
Apparently you did because you worked ahead. Alright, so what do you think the answer is to number 4? Because it looks different.
Sorry, I didn't come back.
Okay. So what do you think the answer is to number 4?
2.
2. You're right. But we need to know why. So this is a base raised to an exponent. A base raised to an exponent always equals some kind of answer, doesn't it? Now look what happens if I switch forms here. This is a base to an exponent equals an answer. It's an exponential form. If I switch to log form, it becomes log base e of a equals ln of 2. Guys, do I ever write log base e? No. What is that? It is ln, isn't it? Log base e is natural log. The only way that natural log of a can equal natural log of 2 is if a is 2. The answer is 2. This is why. Okay? But what happens is we do so many of them is that when I give you a problem like e to the ln of y, you're going to go, the answer is
Why?
y. And you're right. The answer is y. But we need to understand why the answer is y. Okay? Now, this one's a little trickier. If you were just glancing at it and trying to pick an answer, you might start with 2, and you'd be wrong. And then you might go, ooh, 2 times 3 is 6. You're still wrong. Does anybody have an idea of the right answer? You got 8? You got it right. Yes. Why did she get 8? Because what can we do with that number? It actually can be rewritten as a power. So now we have e to the ln of 8, and the answer is 8.
She got smart.
Alright. So how'd you do on your homework?
You got 2 right?
Alright.
Yeah.
Okay. Now, when I wrote these notes to start with, I decided, hey, my students are awesome. Let's not give them any examples and see what they can do. So I turned this into a you try. Let's see what you can do.
I'll probably do pretty good.
I bet you
I've already
will.
done that.
Use your properties. Base E is no different than the other bases.
I have an answer, but it's strange.
My answer is in terms of E.
My answer's in terms of E, but it's still weird.
Okay. Okay. Did you condense this side?
Yes.
Okay. It's both log base E, it's natural log, so we can condense it. And that subtraction turns into division. Okay. And now we have it down to a single log. And when we write it, when we have it down to a single log, we can switch forms. So what is the base when it's natural log? E. So it's E to the first equals 8x over 5. And then we just multiply by the reciprocal. So it's 5/8 E.
Could you also write it like 5/8 and then parentheses next to E?
Sure, you could write it 5/8 E.
Yeah, that's how I.
It's the same thing. Yeah. Okay, and that's our exact answer. We could actually punch that into our calculator and come up with a decimal approximation, but that's a nice, beautiful, exact answer. Okay. I'm so excited because we're about to work the problem that I have given you like 7 times and we never knew what to do. Are you ready?
Sure.
2 to the x equals 5. Now, we already know one exact answer. One exact answer would be log base 2 of 5 equals x.
That's what I was talking about.
That is one exact answer. The problem with that exact answer is written like this. We cannot find an approximate answer.
So I have to change it.
So we're gonna do something different now. We're gonna take this and we're gonna solve for x. We are solving for an exponent. What equals an exponent? A log. So what I'm gonna do is I'm gonna take this problem. I'm gonna show you 2 ways to do it, and then I'll tell you which way I always use. I'm gonna take the log of this side, and I'm gonna take the log of that side. Because whatever I do to one side of an equation, I must do to the other. Now, what did we learn from our properties that we can do with this x?
Seven equals to each other.
We can pull it out in front.
Which is exactly what I said.
And you divide by the log. What do you think?
I don't know, I saw the exponents
And then we get x equals log of 5 over log of 2. Now, the reason this is helpful is I took a problem that was in base 2. Do you see the original problem was in base 2? And I converted it to what base? Base 10. Don't you have a log base 10 button on your calculator? Yeah. So we took something that we can't approximate on our calculators and turned it into something that we can.
So maybe that's a way to do it.
It only works on some operating systems. It doesn't work on all. What do you think example 2 is?
Honestly.
All right, did you get 2.322? Did y'all catch that in?
I don't even find out yet.
The log button?
Should I use my graphic calculator?
Yeah.
Oh, that's probably why.
Okay, do make sure you close your parentheses right here. Okay, now, Yukimi does it the way I do it.
Your head.
Okay? So, it's instead of taking the log of both sides, I actually take the natural log of both sides. And it's not because I'm more partial to base E. It's because I like to be concise. And this one has 1, 2, 3 letters. And this one has 1, 2. Okay? So, alright, so when you take the natural log of both sides, this is what you get. And the x comes out in front. So x equals the natural log of 5 over the natural log of 2, which you will be amazed and astounded when you enter into your calculator. It's the exact same thing.
Why did you put 5 over again? I forgot why.
I'm solving for x. So to solve for x,
You divide by it.
right, we have to divide by that. Okay, now, this actually is using something called the change of base formula. Yep. Now, this is a formula that you can memorize, but there's no need to take up that little spot in your brain. Because a lot of times when we memorize formulas, when we have to recall them 6 months later, we're like, oh, it's log of something over log of something. I remember. And that's all you remember. And you can't go any further. But if you know what to do, instead of memorizing a formula and plugging it in, that stays in your brain a lot longer. So, I don't use that formula. But my work takes you there. Because this formula comes from this work. The proof for this formula comes from a proof of that work. So, I don't memorize the formula because there's no need. The proof of the formula, no. No, I'm not going to do that to you. Now, this problem, you guys could have done that before I taught you this. Because you know how to rewrite 2 as 2 squared, and 8 is 2 to the 3rd. And then what we did over and over and over again was once we rewrote them with like bases, we would set the exponents equal and solve. Now, we like this way. The only problem is this way doesn't work when we can't write them as like bases. Now, I'm showing you this way again to prove that this is the truth. We know this is the answer. And let's see what happens when we do it this way. If we take the log of both sides, or the natural log of both sides, the x comes out in front. And you guys can just watch this. You don't have to write this example. We divide by natural log of 4. And punch this in, please. What is natural log of 8 divided by natural log of 4? Oh, 1.5. What is, oh yeah, got the same thing, didn't I? And just to prove my point a little further that these properties work too, I'm going to take 8 and 4 and rewrite them as 3, 2 to the third, and 2 to the second. And then I'm going to pull this out in front, proving this property. And then pull this out in front. And what happens with the natural logs of 2? They cancel. And what are we left with? 3 halves.
Which is 1.5, which is also.
Okay. So this is where everything comes together. And guys, you just missed this critical part of the lesson, because this is where we tied it all together. Okay? So you can go back and watch the video for this part. All right. Okay, so you try. It's pretty cool, isn't it? A little bizarre.
It's unique. It's really different virtual world.
Thank you.
You're welcome. Okay, so I'm going to show you if we take the log of both sides. Okay, so there's one exact answer. Here comes another exact answer.
Will you be specifying on our test strip this was an exact or
I'll probably ask for both.
okay.
Unless it's on, like, if it's on a new calculator page, I am looking for this or this. The actual third exact answer would be log base 7 of 20. But that's a little bit meaningless, but it is the third exact answer.
It makes no sense.
Okay, so the decimal approximation for this, this, and this is 1.540. Guys, that's 3 decimal places. 3 decimal places, that's the thousandths. Yes, yes. I got to make fun of 6th period today. That was fun. Okay, now the reason I require this, and this is where I caught 6th period, was what they were doing was they plugged in 1 and it wasn't big enough. And then they plugged in 2 and it was too big. So then they plugged in 1.5. Ooh, I'm really close. And then they plugged in 1.55. Ooh, a little bit too big. So then they plugged in 1, and that's how they came up with their answer. Now, I will not accept guess and check. Yeah, you know what?
Why would you do that?
If you're in a testing situation and you're, if you totally forgot how to do it, I get it.
Yeah.
But I am testing, do you understand this process?
Oh, I
Not just do you get the answer right. Because this process we're going to use for something else.
The whole time.
So math is just like one big puzzle, and every day I give you one piece. And yeah, that factoring was a huge piece of the puzzle, wasn't it? So we have to get all the pieces to put the whole puzzle together. All right. So, this is where you get bad at being, and I'm sorry. I'll go ahead and say it. So when we have problems like this, when I told you we started off with a population of 143,000 people, and that population is decreasing 4% per year, and I said, when will the population hit 100,000? And so you had to enter this for Y1, and then you entered this for Y2, and then you had to make the window work, and then you had to intersect. And then some of you were terrible with the graphing calculator. And so it took you forever to find the intersection because you can't figure out how to make the window work. Guess what? We don't have to. Okay? So we don't have to, and actually we should not solve these problems by graphing anymore. Okay? So here's the same problem we did, but we're going to solve it algebraically now. And it's so nice and pretty and easy and exact. It's awesome. So we started off with 143,000 people. So this is just going to be in thousands of people, obviously. Okay? And we want to know when the population will hit 100,000. So we want to know when P, the population with respect to time, is 100,000. But since I have it in thousands, I just put 100. Okay, does everybody follow me? All right. Now, the only thing we have here is we have something extra. When we took the log of both sides, we started off with just an exponential equation where we had a base raised to an exponent equal to an answer. We got something extra. What's extra?
143.
The 143. And how do we eliminate that?
Divided?
Divide by it.
And then you let the log of 4%.
Okay? So, now it's in the right form. So now what we're going to do is leave this 100 over 143. We're not going to change that to a decimal, because if we do, we're rounding, which produces an error. And if we take something that has a small error in it, and then we perform multiple operations with that error gets bigger and bigger and bigger until we could be way off. So we're just going to leave it just like that. And we have 0.96 to the t. Okay? So what do we do? What do we do? What do we do here? We're solving for t. We have it in exponential form. Now, what do we do to both sides?
No, you put it in back. You put it in the log.
Do we take the log of both sides? We take the log or the natural log of both sides. It's the exact same problem here, but here we had 7 and 20. We had two numbers. Here, we have 100 over 143, which is a number, and 0.96, which is a number. These numbers are ugly, but they're still just numbers. All right, now when we do that t comes out in front. So we have ln 100 over 143 equal to t times natural log of 0.96. So how do I solve for t? Divide. So what I'm actually punching into my calculator is natural log of 100 over 143, close my parentheses, divided by ln of 0.96. And so now we get a nice, beautiful decimal approximation. 3 decimal places, please. Okay, now we're word problems, and when we have word problems, we need to give our units for our answers. So this is time per year, so this is time in years. We need to get that unit of measure. Okay? The last one we're going to do is a half-life problem. But we're going to do it exploring a new formula. This is, if you were in a science class and you were talking about half-life, this is the formula they'll use. Yeah. And it looks scary because it's new, but there's nothing really scary about it. Let me tell you what all this stuff means. This N of T just means how much, the amount of the substance that remains after a given amount of time. After 5 years, how much is left? After 3,000 years, how much is left? The amount of the substance left after a given amount of time. That's what N of T means. N sub 0. This sub 0 means at time 0. So this means the initial amount of the substance we started with. What was the initial amount? Okay, E is our good buddy E. It's just our number, 2.71828 approximately. All right, now K stands for our decay rate. How does this substance decay over time? That's what it describes, the rate at which this substance decays over time. And T stands for time. Now, in this case, the substance we have has a half-life of 5,730 years. A half-life of 5,730 years. Now the question is, when will we have 15% of the original amount remaining? How long will it take us to get to where there's only 15% of the original? So, there are 2 steps to these problems. We want to solve for time, but in order to solve for time, we have to figure out how does this substance decay. So step 1 is to solve for your decay rate. And if they give us a half-life period, we can do it. So to solve for the decay rate, they didn't tell us how much we start with. So when they don't tell us how much we start with, I say 100%. We started with 100%. What number represents 100%? 1. Well, this is half-life. So what is half of 100%? 50%, or 0.5. So my initial amount is 1 to represent 100%. My remaining amount is 0.5, or you could write 1/2 to represent half of it. Now, e to the negative k. K is what I'm solving for. That's that decay rate. I actually know the time. It tells me the half-life period is 5,730 years. So that is actually how long it would take me to get to a half. So right here I can plug in 5,730 and I can solve for k. Now, once again, this looks ugly. But it's really not. Because to get it in the right form, we divide by 1. I did it. Okay? And then, because it's base E, what kind of log am I going to take? A natural log. Okay? So over here I have natural log of 0.5 equals negative 5,730k times ln of E. Still looks ugly, but what is ln of E? 1. Goes away. Because multiplying by 1 doesn't change anything, right? So to solve for k, I just divide by this. So k is ln of 0.5. And you don't have to write the parentheses unless you're entering it on the calculator. That's k. Now normally we wouldn't leave a negative in the denominator. We'd either throw it out in front or we would throw it up in the numerator. You can pick. Now, that was step 1. Step 2 is to use that decay rate to answer the question. So with these problems, the first thing we're always doing is finding K, and then we have to use K to answer the question. So the question is, not will half remain, when will 15%? So instead of 0.5 right here, I'm going to put 0.15. I want 15% of the original 100% left. Now, once again, we will not turn that into a decimal, because if we turn it into a decimal, we will round and have some error, won't we? And then if we do more calculations, we will compound that error and make things worse. So we don't do that. All right, so we're going to take the log of both sides. Actually, I'm not taking the log. What am I taking? Natural log, because there's already a base E. All right, so what happens to this exponent? It comes out in front, right? So we get negative ln of 0.5 over 5,730 times t times ln of e. But what is ln of e? 1. It's like it's not even there. And so t is this really weird looking, ugly, exact answer. Because we have to divide by that. Oh, wait a second. Shame. Who knows what I did wrong all along?
You can't have a negative.
Okay, this was a negative k.
It's going to be positive.
And when I plug in a negative, the negative and the negative make a positive. Shame on me. I apologize, folks. I don't know why it took me that long to catch it. Woo! Close one. And you're going to need these parentheses right here. The big ones. Whenever you punch in log or natural log on your calculator, it automatically opens up parentheses. Just close it for them. Okay, so this is an interesting answer, and it's huge.
This is where I gave up. I'm looking. Number 25 is on Chernobyl.
Okay, guys, the other way we could have written this is multiplying by the reciprocal here, but this is good because you got a calculator. So you should get approximately
15,682.813.
Is that what you got?
Yeah.
Oh, that was a .15.
Yeah. All right. So tonight's homework is out of your textbook. It's written on the board. It's in Blackboard, and it's on Willoughby World.
It is all.
It is. And today is the 9th. If you check Willoughby World,
How'd you get that
you
answer?
look under Thursday. Okay.
There's a real good Chernobyl.
How'd you get that?
How'd I know?